thank you guys for coming because these are always the first cuts of the new material, and unless Gary puts the pressure on me and makes me do this, it just doesn't happen. And 7 years later, you have a CBCT textbook. So this section is a little bit thin in there, but I'd like to flesh out some more material. And where's Ken? So Ken gave a standing room only presentation at the AAE last year. I mean, it was packed. And we put in again for a second presentation this year. Ken's going to be the lead. But we have 2 or 3 hours, I think, to fill. So a lot of this stuff is going to be pilot material to see what works in terms of teaching this and what doesn't work. So I hope to have some conversations online after we're done with this and what worked, what made stuff land for you guys and what didn't. And first pass, this is 90% new material, so it's a little rough. They say don't apologize in advance, but I'm doing the best I can with it. So this is new stuff. So you got 3 teeth that come in. And is the mic working enough? Good. So we have these 3 patients with these 3 different teeth that are coming in. And you guys know this stuff already. We just need to tie language to it so that you can see it outside of the narrow domain that we have as clinicians. Good clinicians are natural Bayesians. They naturally think about these things. And if we look at these 3 teeth, it's pretty clear before we do any testing what the likelihood of each one of these teeth responding to cold is. So the tooth on the left, what is the probability that that tooth is going to respond to cold? It's 0. And so if you test that tooth to cold, do you believe the outcome if the patient says they feel it? Who believes it?
If they say they feel it, I believe it.
On the soft tissue, maybe. But compared to the tooth on the right, if you test that tooth to cold, they're far more likely to believe it. So looking at just this range of calcified teeth here, the prior probability, we're going to dive into this right away, the prior probability of a response to cold is very different across these teeth. And when the patient reports a response to cold, that's the evidence, their report of the response. We weigh that differently in terms of arriving at the actual probability, the posterior probability that the tooth actually responds to cold. So the tooth on the left, you might put the cold on there, and it doesn't respond to cold. And that fits what the prior probability is. And we really don't have a good estimate as to whether the tooth is vital or not. The tooth on the right, you put the cold on there, and you would actually expect them to respond to cold because your prior probability is high. And when they don't, then all of a sudden you're scratching your head. So you have the same likelihood. The case on the left, you put the cold, they don't respond. And you're like, your posterior probability, the chances the tooth is vital are really unchanged. You really don't know. Yet the tooth on the right, you put the cold on the tooth, and they don't respond. All of a sudden, you're really now questioning the vitality of the tooth. Good clinicians do this naturally. What we need to do is we need to tie in this lens of looking at prior probability, the evidence that we get, and then the ensuing inferences we make, the posterior probability, across a variety of domains. So we're going to look at that across a few domains. So this is a paper, I've posted this before, why clinicians are natural Bayesians, why good clinicians are natural Bayesians. Clinical diagnosis ultimately rests on the ability to interpret diagnostic tests. But what's a test? Blood tests, radiography, biopsies, technology. And in the final analysis, Ken, everything's a test. So the paper goes on to talk about the interview process with the patient. You ask this question, yes, no. That's a test. Or maybe it's not a yes-no question. You get more or less or somewhat or more often or less often. So you get these kinds of values. But you can start to look at everything as a test where you're going to modify, all right, I have an idea of what's going on, and then you're going to ask a question, and that's going to elevate or reduce the chances of various competing hypotheses about what's going on with the patient. So good clinicians do this naturally. There is, I mean, a host of cognitive biases. The inferential engine is really complicated. There's lots of moving parts to it. We've got clinical trial design. We've got a bunch of issues, samples and sampling, that are running this inferential engine. But we're going to focus on the three central pieces of the inferential engine: the prior probability, the likelihood, and the posterior probability. So these three gears in the middle are the gears that we use on a day-to-day basis as clinicians. And when one of those gears is missing or isn't working, the whole process breaks down. So a way to think about this is that there are three gears that are turning. The prior probability gear drives the likelihood gear, drives the posterior probability gear. We have to think about all three of these gears. And when we're missing the middle gear, or we forget about, this is what usually happens, we forget about the first gear, our estimates get all messed up. Like I say, as clinicians, when we're doing clinical examination and testing, oftentimes we are able to take that into account. But when we extend that outside of domains to cone beam CT, which we talked about in 2010, probability, 2011, tests and testing, 2011, we're not well versed in these areas. We have a somewhat intuitive understanding of them, but we need to develop a better understanding of them. This was samples and sampling, so we haven't actually talked about this stuff at TDO for quite some time. So Gary wanted me to talk about and see if I could put something together that would tie these three concepts together across a variety of domains outside of clinical testing that we did in our first example. So I'm going to do the best I can for you guys. And like I say, I really want to know what works and what examples didn't work. So why most public endodontics research is false. Humans don't deal with probabilities very well. Humans don't deal, and this includes me. This includes me. Humans don't deal with conditionals well. If this, then that. Tests, testing, decision-making, research are all conditioned, note the word, on both of these things, having an understanding of that. Years ago, we did the Monty Hall problem. Who remembers that? Do you switch? I mean, everybody knows that we switch now. And we're actually going to do a simpler problem. The Monty Hall problem is where you pick a door and he shows you a goat, and the question is, do you switch or not? And the answer is you switch. Let's even do a simpler toy problem. This is called the boy-girl problem. Who knows this problem? Good. So, you're going down Strand Way and you bump into somebody, a colleague maybe you haven't seen for a long time, and you start chatting him up, and he says, I have two children. At least one of them is a boy. What is the probability that the other is a boy? And I'm up here, so it's a setup. It's a setup. So when that system one answer comes to mind, you need to go, sit down, and recognize the form of the problem as a conditional probability problem. Okay, so that's one of the skills. And I don't have that across all domains, but I have it fairly well in our domain. That's in system one for me right now. I can see those things. But outside of my domain, the boy-girl problem, I had to sit there, and it was like an hour to pen this thing out, figure out how to do that before I looked at the solution to this. So system one comes up with the 50% automatically. It's like the ball and bat problem. It's the same kind of thing. If the ball costs this much, how much is the bat? It's a conditional problem. This is actually a conditional probability problem. We want to learn to recognize the form of those problems and tell system one, sit down. Let me see if I can figure this out, because that intuitive answer gets checked off by system one as being plausible. It makes sense, but it's wrong. Okay, but it's wrong. So you bump into the guy on Strandway, you chat it up, he's talking about family, you haven't seen him for a long time. I have 2 children. At least one of them's a boy. What is the probability that the other's a boy? 50% comes to mind, right? Everybody. Yeah, that would be wrong. Okay, so that's what he tells you. So we can compute these conditional probabilities with Bayes' theorem and the explicit version of Bayes' theorem, and Gary told me not to do that, so we won't. What do we want to do? And Gary's done some lectures on this as well, is sometimes you just want to draw it out. Okay, sometimes that's all you really need to do is draw it out. All right, you meet a guy. What's the first thing that he tells you? Lena. I have 2 children. So, I have 2 children. And you don't know at that point what they are, do you? So what are the possibilities, Ken, for 2 children? Good. Okay. So there's 4 total possibilities. Thank you, Charlie. Okay? 4. 4. 4. Charlie, there's 4. So this is important. I'm right about this. There they are. So this is important. I'm right about this. So what we want to do, as we've done on TDO for a really long time, is don't argue with me about it. Try to understand it. Okay? And the reason I'm right about this is I'm not that smart. I'm taking these examples from guys like Roger Lewis and John Ioannidis and those kinds of things that Paul Segari told me not to do. So you actually have 4 possibilities. You have 2 boy-girl possibilities. You have boy-girl and girl-boy. So there's 4 total possibilities when you consider ordering of the children. There's 3 possible groupings. 2 boys, a boy and a girl, times 2, and 2 girls. Okay? So there's 4 possibilities. You got to draw it out. So you draw it out. So he tells you, I got 2 children, at least one of them is a boy. What do we know now? It's not girl, girl. Okay? It's not girl, girl. So what is the probability that the other's a boy? There's 3 other possibilities. It's a third. How can that be? There it is. Ivan, are you awake? Okay, good. I didn't see you there. And another way to maybe convince yourself of that is all right, so I did a spreadsheet. And every time I click on this spreadsheet, it'll recalculate the number of boy-boy families, the number of boy-girl families, the number of girl-boy families. Can you guys read that, or do I need to make it bigger? Is that better? Okay, good. All righty. So this is the total number of families that we're going to have. Let me fit that. Is that legible now, somewhat? Okay. So every time I click on this, this is a random sampling of 1,000 families. So if I click on this, you're going to see these numbers change. So this actually landed on 250, 249, and you can see there's a little disparity between them because this is just, there's 1,000 families. There's going to be some natural variability of it. And we can look down at the bottom of the spreadsheet. There's family number 1,000 down there. Okay? So I'm going to click up here, just click on the column separator, and you're going to see these numbers change. And they'll just vary just a little bit, but there's always 1,000 families. So if you think of a collective of 1,000 families, this may help you get a better insight onto the 1/3 probability of boy-boy. So here's the boy-boy families, and we can see there's about 250 of those, 250 boy-girl, 250 girl-boy. Again, these are considering ordering effects. And 250 girl-girl families. So out of we might think of this as out of 1,000 families that are like this, what is the probability of the boy-boy? It's going to be 1/3 because the girl-girl family is eliminated. Does that help a little bit? Does that example work a little bit? Okay. You can just click on it. It'll be a little bit different every time, but we'll see the ratio is about the same. Now, if it was an infinite number of families, it would be perfect. or a million or billion families. It'd be pretty close. Okay, so the boy-girl problem. And so that was a pretty simple, what we call these toy problems. And, when I heard it, it's the same as the ball and bat. 10 cents comes to mind right away. 50% comes to mind right away. But I recognized it as a conditional probability problem. And I sit there and figure it out and draw the whole thing out. A more interesting one is to ponder is you meet your buddy on Strandway and you're chatting it up and he says, I have 2 children. We'll work this out online. I'm going to leave it for something for you guys to think about. I have 2 children. At least one of them is a boy who was born in the summer. What is the probability that the other is a boy? What the hell does born in the summer have to do with it? Right? Nothing. That's what System 1 says. Nothing. But we recognize the form of the problem as a conditional probability problem, and we need to go, wait a minute. I don't deal well with conditional probabilities. Maybe I need to think about this a little bit better, a little bit more. So we can play around with that one online. So I only have 1 or 2 clips from experts, and this one from Otis Brawley ties right in with that. Like, we don't know as much as we think we know.
I was educated as a Catholic, and I went to Catholic schools, and was very influenced by several Jesuits in high school. One of them, Father Polakowski, used to always say, remember what it is you know, what you don't know, and what it is you believe. And when I went off to medical school, he said, remember, doctors have a tendency to confuse what they believe with what they know. And I found that to be incredibly, incredibly true.
So what I've found, and we all do this, it's what we know that just ain't so is a big problem in medicine and healthcare. So research. So why most public endodontic research is false? Why root canals cause cancer? We've all heard this. I think Cotter just posted something along these lines. We've heard 97% of terminal cancer patients previously had this dental procedure. And I was delighted to log back onto TDO after a month or 2 of being off and see that this actually just got posted. And several people now, and this is different from when this got posted back in the day, replied, well, 100% of them drank water, and 100% of them breathed air, and 100% of them ate lettuce, and that's probably what caused their cancer, was eating lettuce. So we have some better responses now to identify these kinds of inferential problems. We're going to take a look at this a little bit through cancer, through lung cancer and smoking. And these old ads, look at this little girl. It's just stunning that they did these things, and these are from the 50s. Dad, do you remember this stuff? Yeah. My dad's here. Morning, Dad. So more doctors smoke Camels than any other cigarette. Doctor's Choice is America's choice. The T-zone test will test you for your throat. Okay. And then Cotter just posted this on TDO. Shocking discovery. 90% of terminal cancer patients have had this procedure. How do we think about these things? What's the proper responses to these things to be? And as Sandra pointed out a couple of years ago, was it 2 years ago, Gary? 2 years ago, Sandra pointed out, says, you need to pay attention to these people. Because while they may be quacks, they may not be. Okay? There may be some merit to some of the things that they say. So who knows Ronald Fisher? Everybody should know him, right? This is that Fisher, the Fisher that wrote statistical methods for research workers and developed p-values and all that kind of stuff. So Fisher talks about a remarkable piece of research carried out by Dr. Bradford Hill. This is in 1958, and his colleagues at the London School of Hygiene. We heard indeed that it was thought that he had done a remarkable discovery to the effect that smoking was an important cause of lung cancer. This was like new back then. The first inquiry, Dr. Bradford, was to take about 1,500 patients in a number of different hospitals who had been diagnosed as suffering from lung cancer. Of course, the diagnosis is normally aided in recent times by the use of radiology. Woo-hoo. The lung cancers are perceived by their shadows when an X-ray is passed through the lungs. So let's just take that at face value and start to play around with some numbers to see if we can make some sense of this. So 1,500 patients with lung cancer. How would we go about establishing that there's a relationship between lung cancer and smoking, or even a causal relationship? Maybe just a predictive relationship, but maybe a causal relationship. So let's just make up, we're going to treat this as a little bit of a toy problem, then we'll actually get some real numbers in there. But it's a toy problem to start with. Just say half of the patients are smokers. So 750 of the 1,500 patients are smokers, which is probably not unreasonable in 1950. Dad, did you ever smoke? How many of your friends smoked? Yeah. Give me an estimate. 10, 50, 90%? Working at a restaurant? Jesus. Everybody hear that? Table of 6 puts 3 ashtrays, cleans a tray every 10 minutes. Oof. So this is 50s then, isn't it? 58. That's when Fisher wrote this article. Yeah. Yeah, 1958. So this is maybe not as far-fetched as it might seem. And we're in California now. And I might point out that people that go to a restaurant out to eat, especially at night, do you think they may be, from a prior probability standpoint, more likely to be smokers or less likely to be smokers? Do you guys go out? Jason's LDS. Do you guys go out, party of 6, to restaurants on a Friday night? Nope. So we might want to interpret that as those people may be more likely to smoke. We don't know, but we want to think about what are the other factors that might contribute to that observation, because that's all we get to do is get the observations. So 750 patients are smokers. 97%, this is in London, right, are tea drinkers. And so we infer, right, drinking tea causes cancer. But if we think about it a little more carefully, they're all water drinkers. And so we want to be careful about making an inference in that direction. There are ways to do that, and we're going to learn how to do those. And that's one of the things we want to think about is what is the chances that the 6 people that come out on a Friday night and go to a restaurant, is that an increased chance that they might be smoking or decreased? And we may not know that, but we want to be thinking of that and asking that question, because that's a prior probability issue. So what we really want to know, and we're going to have to learn some of the language of probability to talk about this. We're going to have to learn to read these things. So we're going to do some read aloud exercises as we go this. I want you guys to get the hang of how to read this notation. It's just like reading endodontic notation. It's not that complicated. It just looks foreign. Gary, don't you think this is important? To learn how to read the notation. And so we got to do it. Let's do this out loud. We're going to do it on a bunch of them to get the hang of this. So we're going to read this as the probability of cancer given that you're a smoker. Let's do it out loud, everybody. The probability that cancer given that you're a smoker. The probability of cancer given that, that's what that vertical bar means, given that you're a smoker. So 1,500 patients with lung cancer, about 750 patients are smokers. Let's read this out loud. The probability of being a smoker given that you have cancer. The probability out loud. Probability of being a smoker given that you have cancer is 50%, given that. So we want to learn to read this notation because I can't fit the stuff on the slides. Now we're reversing it. The probability of cancer given that you're a smoker is 50%. So I just set those in. We're just practicing reading the slides now. The probability of cancer given that you're a non-smoker is 50%. Okay, we're just making these numbers up right now, just practicing reading the slides. Okay, so we've got some numbers here. What we really want to know, though, is, let's read this one out loud, is the probability of cancer given that you're a smoker greater than the probability of cancer given that you're not? That's really the question we're interested in, isn't it? Without establishing a causal relationship, Because there may be other habits that make you be a smoker that also give you lung cancer. And Fisher actually argued for that. But what we have to establish first is that there's at least a mathematical relationship, and then we may look at a causal relationship between those two. So in shorthand, we're going to use the probability of, this is very bottom, probability of cancer, given that you're a smoker. This is the question we want to ask. The probability of cancer, given that you're a smoker, is that greater than the probability of cancer given that you're not? The little tilde means not. Everybody do that out loud. Ready? Probability of cancer, given that you're a smoker, greater than the probability of cancer, given that you're not a smoker. Okay. Okay, so that's given that, and that little tilde means not. There's a variety of ways that those are used, and that's the easiest way I could do it. So playing around with our toy numbers, we might think that with 1,500 patients with lung cancer, maybe half of them are smokers. Maybe 10% are smokers. Maybe 97% are smokers. Do you think that if there were 1,500 patients with lung cancer and only 150 were smokers versus 97% of them were smokers, do you think that might make a difference? It would seem like it, we don't know, but it would seem like it might make a difference. You know, if 97% of the people with cancer were smokers versus only 10% were smokers, it would, you'd kind of go, God, maybe there's something there, right? What else do we need to know? Jason, base rates. Base rates. What's a base rate?
Like how often it occurs.
In the population at large. Let's use the right language, the prior probability of smoking. Okay? So what we really want to know is, we know that, let's just making some numbers up, the probability of being a smoker, given that you have cancer, maybe 50, maybe 10, maybe 97, just playing with some numbers. But what we really want to know is the probability of getting cancer, given that you're a smoker. And what we really, really want to know is, does that increase the risk? So again, thinking about it, if there's 750 smokers out of 1,500 cancer, and there's 750,000 smokers out of the 1 million people in London, does that sound different than there's 750 smokers out of the 1,500, so half of them, versus only 10% of London smokes? Does that look different to you? If 3/4 of London smokes, and there was no relationship between smoking and cancer, how many people would we expect to be smokers, given that they have cancer? 3/4. There was no relationship. So if there was no relationship between smoking, we got to dwell on this a little bit till I'm sure everybody gets it. If there was no relationship between smoking and lung cancer, we would expect to see the same proportion of people smoking that have cancer as are smoking in the population, if there was no relationship. Okay, so that's this upper portion right here, is the percentage that are smoking that have cancer. It's 50%. Here, however, we have 75% of the population that are smokers, but only 50% of the cancer patients are smokers. Does that make you scratch your head a little bit? What might that hint at? Say it, Jason. Smoking reduces your risk of cancer. Because if there was no effect, you'd expect 3/4 of the cancer patients to be smokers. Now on the bottom, we have only 10% of the people that smoke, yet half of the cancer patients smoke. What might that hint at? Maybe there's something that those people are doing that increases their risks of cancer. So these are called the prior probabilities. Before we know anything about them having cancer, before we know anything about at least one child as a boy, what's the probability of all the various outcomes? Well, here the probability is there's a 3/4 chance that that person smokes. And on the bottom, there's a 10% chance that that person smokes. So this actually would seem to like maybe influence the probability that smoking and cancer are related. So we're going to reframe those ratios in the language of probability. Another read aloud. The probability of being a smoker, given that you have cancer, is 50%. And here, the probability of being a smoker, we're talking about given that you live in London, because this is London, the probability of being a smoker in London is 75%. So this is the prior probability, or the base rate, or the prevalence of smoking. Is this starting to make a little sense? Yeah? Okay, good. So that would seem to be an important piece of information to know if we're going to make this inference about smoking and cancer. 97% of terminal cancer patients have had a root canal. Well, if 100% of people have had a root canal, that doesn't really matter that much anymore. But if only 1% of people have, and of that 1%, 97% of them are getting cancer, maybe we need to pay attention to that. Okay, so what's the prior probability, the prevalence of root canals in that pool? So we have a couple of pieces of information. Now, so we know that the probability of smoking, given that you have cancer, so our cancer patients, half of them smoke, but 3/4 of our population smokes. The probability of smoking is 3/4. We're making these up. These are toy numbers right now. We will get to the real numbers. But it would also seem to be that just the prevalence of cancer in general should affect this. So the probability of getting cancer, given that you're a smoker, should somehow depend on just the probability of getting cancer, period. So if we're going to assign a number to the probability of getting cancer, given that you're a smoker, and say that number is 10%, it would seem like we would need to take into account that the prevalence of cancer, or the probability of cancer at large, somewhere between 0.1%, 1%, or 10%, it would somehow seem we would need to take that into account as well. Because that would change, shall we say, the order of magnitude. If it's the prevalence of cancer is 50% or 90%, that would seem like it should elevate the chances of getting cancer as a smoker. And if the prevalence of cancer is only 0.1%, it would seem like it should lower it. Okay? So it somehow seems like we should need to take into account the prevalence of cancer, or the probability of cancer at large, into our calculations. So we have those pieces of information. And so we're just going to say the prevalence of cancer, the probability of cancer in London is 10%. The probability of being a smoker, given that we've diagnosed you with cancer, is 50. And the probability of being a smoker is 75. Toy numbers, we're making these up. So it would seem like if we want to calculate the probability of getting cancer, given that you're a smoker, if the probability of cancer overall is large, that should go on the numerator. So when it gets bigger, the probability of getting cancer, given that you're a smoker, gets bigger. It would also seem like the probability of being a smoker, given that you have cancer, if that goes up, that should increase the probability as well. And then the probability of being a smoker at large, well, if everybody smokes, everybody that gets cancer is a smoker. And so that should go on the denominator. So we're going to put the probability of being a smoker, given that you have cancer, because if that goes up, that should increase the chances of getting cancer, given that you're a smoker. We're going to put the probability of cancer on the top, and then the probability of being a smoker on the bottom. We'll play with some toy numbers to give you a sense of things. So in this example, for instance, if the probability of cancer, this is the probability of cancer over here, is 0%, it doesn't matter what these numbers are. If the probability of cancer is 0%, what's the probability of cancer given that you're a smoker? 0. It's trivially obvious. It doesn't matter what those other numbers are. So that actually kind of works. So sometimes you want to test these things. If it all went this way or it all went that way, do I get an answer that kind of makes sense? Trivially obvious. 0%. Okay. And if the probability of cancer, so this number here, if the probability of cancer is 1%, but everybody's a smoker, the probability of being a smoker, everybody's a smoker, that means everybody that gets cancer is a smoker. Well, those cancel out, so the probability of getting cancer, given that you're a smoker, is 1%. It's the same as the probability of cancer because everybody smokes. Well, that kind of makes sense too, okay? So these are what I'll call trivially obvious programs, just kind of as a check. This is like the ball and the bat problem. You guys all remember that one, right? If all we did was add $1 and $1.10 and 10 cents, we go, it's $1.20. That's the wrong answer. So sometimes you just got to do these trivially obvious checks. Make sure, does this make any sense? Okay. Now, let's do a more interesting example. Let's say half of the patients with cancer smoke. The prevalence of cancer is 1%. And 99% of the cancer, 99% of the people smoker. What do you think the probability out here will be? The probability of being a cancer given that you're a smoker is? 0.5%. So here, what happened was we went for an overall cancer rate of 1% here, but 99% of the people smoke. So actually, in this example, smoking does what? Reduces your cancer risk, and it all comes from the base rate. Down here, the prevalence of smoking. Let's go play with some real numbers. So these are some real numbers. I peeled these off of this website. I'm going to make this a little bigger so it's easier to see, I think. Okay. So the probability of being a smoker is 1 in 5. And the probability of lung cancer is 0.1%. And of the lung cancer patients, 90% of them are smokers. And so that actually answers what's our increase in risk? Our increase in risk is about 33 times, okay? If we increase the probability of cancer to 10%, our risk stays the same, but the fixed probability goes up. Everybody saw that, how that happened? Okay, so if the probability of cancer is very small, the probability of getting cancer, given that you're a smoker, is also very small. But the relative risk stays the same. The probability of being a smoker goes to, let's say, 50%. And let's just do the probability of cancer, 10%. And the probability of being a smoker, given that you have cancer, is 50%. It's a wash. So if half the people smoke, half the cancers, so this makes sense, half the cancer patients should be smokers, and there is no increase in risk. If 99% of the people smoke, or even 90% of the people smoke, the probability of cancer is 10%. Half of our patients, half of our cancer patients are smokers. What does smoking actually do? Reduces risk. Reduces risk. So you have to have all three pieces of that puzzle to calculate those probabilities. You have to know the probability of being a smoker at large, which is the prior probability. You have to know that. You have to know the probability of cancer at large, and then you get to add in your evidence, your observational data. That's the actual data that you get to observe when the person comes in to the clinic, and then you ask them, are you a smoker? And then they tell you. So that's the evidence. What do we do? As humans, what do we do? We get it fixed in our head that smoking causes cancer, and we only ask them that, and then we assign the posterior probability to the observation. We don't think about, well, I wonder what the prevalence of smoking at large is. You have to know that to make these judgments. Okay. Okay. So that's toy problem number one. And we actually just worked out Bayes' theorem with smoking. So we did that example there. So this example here, if 21% and it's 90% smoke, 90% of the cancer patients are smokers, the actual probability there is, it's a 33 times increased risk. So more prior probability stuff. You gotta have an idea of what you're observing. You're not getting to observe clinically in the hospital, you're not getting to observe the patients who are smokers that don't have cancer. They don't come in, okay? So we want to be very careful about, okay, what are we observing? What are we not observing? The patients that are smokers that don't have cancer, and actually the larger number is the patients who are smokers that don't get lung cancer. And we're also not observing what is the prevalence of smoking at large. So here we have another ad from the 1950s. Chesterfield, much milder, is best for you. And meet Miss Rita Tennant, secretary who recently made the 30-day test of camel mildness under the observation of a noted throat specialist over here. And then a medical specialist is making regular bi-monthly examinations of a group of people from various walks of life. 45% of this group have smoked Chesterfields for an average of 10 years. What's wrong with these? What's wrong with these statements? I mean, we're looking at them through the lens of what we know now about smoking. What's wrong with them even back then, and specifically on today's topic? 45% of this group have smoked Chesterfield for an average of 10 years. Pardon? Well, they got it. They had, what's that? What about the other 55%? They die? What happened to the other 55%? So what is the probability that the people that smoked Chesterfields for 10 years, that 45% that they got to observe, versus the other 55% that they didn't observe? What the hell happened to them? Okay, on Rita, meet Miss Rita, who recently made the 30-day test of camel mildness under the observation of noted throat specialists. What about the other 999 patients who didn't make the 30-day and quit? What happened to them? So the observations here sit on the 45% of the group that smoked Chesterfield for 10 years. Well, are they more likely or less likely to have throat problems? They've been smoking for 10 years. I would think, I don't know, but I would think that they would be less likely. What we got to do is we got to have that. We don't have to have the answer. We just have to have the awareness. What happened to the other 55%? Who am I observing? I'm not observing the people that died. I'm not observing the people that were fine. 45% of this group smoked Chesterfield for 10 years. We don't know about the other 55%. We would never do that in endodontics, would we? Oh, thank you, Shimon. Of the 350 patients and the 405 teeth treated, 109 patients with 128 teeth were excluded as discontinued, 9 deceased, not relocated. There's a sample of 277. Of the sample, 106 teeth. 21 teeth had been extracted, 11 because of periodontal disease. So what happened here? We only observed the teeth for apical periodontitis that were actually still in the head. We only observed the throats of patients of the people who smoked Chesterfields for 10 years. We only observed the 30-day trials results on the patients who actually completed the 30-day trials. The people whose throat really hurt and stopped at day 2, we didn't observe, or they died. We didn't observe those. So the common way we talk about this in medicine is counting death as a good outcome. We've talked about this, but this is a prior probability issue. The chances of the 10-year Chesterfield smoker's throat being fine are elevated over the 55% that didn't smoke Chesterfields for 10 years or died. I mean, the dead people probably don't have throat irritation. Okay. Do you see how it works? So we got to look at, okay, what are we observing? Who got clipped out of the sample? And what's the probability that they might have an outcome of interest? That's a prior probability before we actually look in their throat. They smoked Chesterfields for 10 years. Before we looked in their throat, there's probably a decreased chance that they have throat problems compared to the people who have not been smoking Chesterfields for 10 years and quit at year 5 because their throat hurt. Prior probability, before we did the examination on them. Before we did the examination here, the extracted teeth, the really fifth of the teeth that were extracted, what do we think that there was an increased chance that those had apical periodontitis over the teeth that remained in the head, or decreased? Decreased. So the actual success rate goes from 81%, which is reported, to 69%. Because what happened here is all the extracted teeth counted as a good outcome. They counted as successful. Prior probability issue. Before you ran throat exam, before you took a radiograph. I started reading this book a bit ago. David Vose, he's the guy who wrote this software. This is an add-in for Excel. This is the software I've been using for years to do some of this modeling. And he actually happens to be one of the foremost risk analysis peoples in the world. And he actually had an interesting chapter in here on testing and modeling causal relationships. Like, how do you determine cause? And Gary, testing and modeling causal relationships is a subject of plenty of good books. I recommend Pearl and Neapolitan and Shipley because they are thorough, fairly readable if you're good at math. You started Pearl, didn't you? Yeah, it's brutal. It's brutal. But this book is actually for Ken, Jason, the people that want to go to the next level, group 3. This book is actually really good because it actually has real world problems. This guy consults to help figure out, okay, we have a herd of cattle, and we know that this percent have prions in them. And we need to test this cattle that we're going to import. How many cattle do we need to test to be 99% sure that, and we're not 100%, but to be 99% sure that the cattle we're importing don't have prions? These are real world problems that people like this guy solve. So it's a really good book on probability because it's super duper applied. So I'm putting it up there for other people if they want to read it. But he has an interesting little bit in here where he talks about testing and modeling causal relationships. And he says, I haven't done the study, but I'll bet the probability of having lung cancer within your life is B if you carry, A, if you carry matches, and B, if you don't carry matches. So we could make the inference then that carrying matches causes lung cancer. And of course, there's no real way to establish a real risk link there, but if you're looking at the wrong thing, carrying matches, and you don't know about smoking, you're looking at the wrong thing, then you could make the inference that carrying matches causes lung cancer if you just are assuming what? Correlation equals causation, okay? So I thought that was a cute little bit in there that tied in with that. So why carrying matches causes lung cancer. And Fisher talks about this too. Steve?
Question, when I remember back to those studies like you were quoting in the magazines and that, they always had thresholds for that. They always had, someone who smokes 2 packs a day, or, someone who does, for this long, or, someone who smokes filter, they always have these little thresholds that would just kind of take your imagination and let you run with it.
So Fisher talks about this, and Vose talks about this as well. And if there's a relationship, you would think, like, dropping names again, like Lewis said when you did that drug study, you would think that if you increased smoking, that should increase your cancer risk. That would make sense. If you increase the drug dose, you should get an increase in effect, that kind of thing. If you increase the apical size, you should get an increase in outcome, or not. Because there might be a point where it just doesn't matter anymore. So there might be a threshold that, smoking a cigarette a week just doesn't matter. It's in the noise, and a little bit of radiation from the dental office doesn't matter. It's in the noise. And there's actually some evidence that, for instance, with radiation, that there's actually some evidence that a little bit of radiation actually may be beneficial. May be beneficial. So maybe a little bit of smoking may be beneficial. Pardon? Like the vegetables. Yeah, like the vegetables. A little bit of vegetables might be beneficial. So, but Fisher talks about this as well, that to really establish those kinds of relationships, you want to be able to vary one and then see the other vary. Of course, some things we can do that with, but I can't randomize you to the 2-pack a day smoker group. We do some of these experiments we can't do, and all we get is observational data, which is why it's so important to understand how to interpret observational data, because that's really kind of all we have. So Fisher writes, again, this is Fisher writing this, statistical methods for research workers. Correlation is not causation. The fact that if two factors, A and B, are associated clearly, positively, with statistical significance, it may be that A is an important cause of B, it may be B is an important cause of A, or maybe it's something else, X, is an important cause of both. And one of the things that Fisher argued was that there was actually a genetic predilection, for lack of a better word, that caused both lung cancer and people to smoke. Now, Fisher was a smoker. So talk about a little and he died of lung cancer. Talk about a little cognitive dissonance on that. So, I mean, and he was a genius level guy, and so these kinds of things, you know, they affect all of us. So right on point, cigarette smokers have a 9-fold greater risk of developing lung cancer than non-smokers, while over 2-pack a day smokers have at least a 60-fold greater risk. Now let's think about that a little more carefully. 2 packs a day, smokers. What's the prior probability that they're gym rats and are thin and fit and exercise? Higher or lower? What's the probability that their BMI is in the middle or low 20s? What's the probability that their BMI, the body mass index, is in the middle or low 20s? Higher or lower? What's the probability that they engage in a whole host of other unhealthy lifestyle choices? Higher or lower? Okay, so we've got to think about, all right, so they have a 60-fold increase in risk, but they're 2-pack a day smokers. That's a different, we call that reference class. That's a different group of people than maybe someone who smokes when they go out for a drink with their friends or something like that, but doesn't, shall we say, buy cigarettes. They bum them, okay? So right on point there seems to be an increase in risk with an increase in this variable, an increase in this variable, but the causal relationship isn't as clear because there's a whole host of other prior probability issues that go along with that we can identify. We don't know, but we can go, God, I wonder about these other things that we think are associated with increased morbidity and mortality. Okay, so Fisher writes pretty extensively about this thing. And Fisher had a long-standing, I would hesitate to say, he didn't like Bayesian inference and Bayes' theorem at all. And he worked, it was adversarial at the least. Fisher tried to develop a method of what we just did with cancer, with smokers. He tried to develop a completely different method for doing that kind of inference and failed at it. And to this point, no one has figured out a mathematically, internally consistent way of going from the things that we can observe. What's the prevalence of smoking? What's the prevalence of cancer? And what is the prevalence, the probability of when you have cancer that you're a smoker? We haven't figured out a way to invert those things yet other than Bayes' theorem. And he tried for a lifetime, and he was a pretty smart guy. Okay, so why most published research is false? So an outcome is a posterior probability. Posterior probabilities are conditional. The conditions are both the prior probability and the likelihood. And we saw, as we manipulated the prior probability, the prevalence of smoking, we could actually demonstrate that smoking reduced cancer, not from a causal standpoint, but from an association standpoint, based on the prior probabilities. So you've got to know these prior probabilities. And this is what led, now so David is a natural Bayesian, David Clark is a natural Bayesian without knowing it, because he's looking at these broken teeth in his practice. It's like, what's wrong here? And I started, shall we say, counting these things in a very, very loose fashion a few years ago. And favorite whipping boy, of course. Thank you, Terry, for always posting things to use. So, so Terry writes, 95% of the general dentists performing endo are horrible at it. He wrote this on Roots. You can just, this is in the public domain. 80% of the endo is done by general dentists. 95% are too clueless to know they are not in the 5%. So what do we have here? What do we have? We have some assertions of base rates. Yes? Yeah. So let's take Terry's assertions of base rates. This is the thing that I talked to him and talked to him and talked to him and talked to him about, but he never understood. That you've got to sit down and do the math. And so these are, the next couple of slides are slides that got clipped out of the New Jersey presentation. But let me summarize this, what we know from Terry. 80% of the endodontics is done by GPs. 95% of that is horrible. So 95% of the 80% is horrible. We can just do the math, and that makes it about 75% of endodontics is horrible, according to Terry. Okay, so this will set the base rates. Let's just assume the remaining 25% isn't great, it's just not horrible. It's just not horrible. So 75% of the endo is horrible. What would we expect to observe from these two different, I want the word, it starts with prior. What would we expect to observe at 20 years from these two different prior probabilities? What would we expect to observe? Okay, so we have two groups. We have horrible here and not horrible out here. Okay, and this slide actually made the New Jersey meeting, the axis of apparent horribility. And this is Terry's, and this is Cliff's, and this is Bellamy's case over here that have what we might talk about, because they're BU guys, as the look. And then over here, there's marginal, not good, not horrible, and heinous down here at the bottom of the curve. So here is our prior distribution, our prior probability of cases with 30%, 25, 30% being not horrible. In fact, we'll give it to them. These cases have the look. And then over here, we've got, on the other side, we've got, actually I'm doing this back, I'm doing it to my screen. Over on this side, we have cases that are horrible, because 75% of the cases are horrible. What would we expect to see if we were going down the road? So if we start with 75% horrible, and this is 1993, so this was the NJAE in 2013. I didn't get these slides in there, but you're going to get them now, because these were fun slides to make. 25% are not horrible, and if we model in, and we say the success rate doesn't matter. So this is one of those where, you know, everybody smokes, so smoking is not important as a cause of cancer. They all smoke. The success rates don't matter. If 50% of the population smokes and 50% of the cancer patients are smokers, it doesn't appear that there's going to be a relationship. If the success rates of horrible versus not horrible cases are the same, what would the mix look like at 10 and 20 years down the road? Jason, what would the mix look like? 75-25. They look the same. So if we go down the road, we would expect to see, and we model in a 20% failure rate with both arms, we'd expect to see the surviving stream of cases in 2013. So this is 2003, and a few died off. And 2013, 20 years later, a few more died off. We'd expect to see the surviving stream be about 75% horrible and 20% not horrible. Is that what the surviving stream that you guys have seen me post over and over again looks like? It doesn't look like 60% horrible and 20% not horrible. It looks like 98% horrible. Okay, so let's play with these, the base rates and the likelihood, the survival, because the survival is the likelihood. How many cases of these make it, our observations? So let's say we start out at 75-25, and we model into that 100% of the not horrible cases make it. There are no failures in the not horrible cases, and half of the horrible cases fail. So the horrible cases have a 50% failure, and the not horrible cases are 100% successful. What does the surviving stream look like? Let's just rough it out. It's about half not horrible cases and half horrible cases. So the stronger we try to make this case that the look matters, actually then the survival and the success rate of those cases is higher, the more it's contradicted by the surviving stream of cases. I have been unable to come up with a prior probability and likelihood, the various splits of horrible versus not horrible cases, and the various success rates of horrible versus not horrible cases that fit the surviving stream, because the surviving stream looks horrible. Let's make it even worse. Okay, so the not horrible cases, 100% of those survive, and the horrible cases, 2/3 fail. What does the surviving stream look like? It should be 50-50 split. So half of the surviving stream should look great, and half the surviving stream should look awful. And that's if none of the good-looking cases fail. It just doesn't look like that. So failing to take into account both the prior probability, which Terry gave me. He gave me that 75% of the endo is horrible. He gave me that. So just taking Terry's numbers and modeling in what Terry might assert, that well-done endodontics lasts longer. The surviving stream seems to contradict that. And I've not been able to come up with a set of numbers that fits the surviving stream based on what we think contributes to long-term outcomes. So David and I made something else up. And you guys all know what that is. Okay? So the surviving stream, you would think that it should look like this, but the cases just don't look like that. These are all 20-plus-year-old cases in here. All the heinous and the marginal and all of that kind of stuff. And you guys have seen me post these. There's one good case here, right? Out of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So out of 35 cases, there's one good case, so it's like 3% good-looking cases. Everybody see it? So there's just, I have to go find these cases that actually look well done at 20 years. The rarest 20-plus-year-old case I have, give me a guess. Maxillary molar, original endo. Maxillary molar with 4 treated canals. Rarer still is the molar that's had periapical surgery. So those are pretty unusual. Most maxillary molars, how many canals were treated in that thing? Ish. This one actually is out now. That one broke. So again, back to prior probability. We got to take into account what that, and so the louder Terry would yell about how bad general dentists were, how bad all the endodontics was, the worse the numbers got for him. Very, very counterintuitive, because you didn't take into account the prior probabilities and their effect on the posterior probability. Even if modeling in 100% success with the good-looking cases. All right. So outcomes. We're going to go back to outcomes a little bit as well. And I'm actually doing pretty good on time. I'm getting some of the material that I wanted. Gary, you need 15, 30? 15, 20? And I go till 10. Okay. Coin tossing. I would talk about directions of logic in my abstract, and we got to get this, because our computer modeling depends on this, and we flip-flop directions of logic all the time. I've got some sections in the textbook on it. These examples and graphics are basically right out of the textbook. So possible outcomes in a 5-flip coin experiment. What we want to be aware of is that we've got 2 basic directions of logic that we use. We have this deductive logic. If this, then that. This, therefore that. And this is yes, no, black and white, end of story. Then we have logic that goes in the other direction, which is the kind of logic that we use day to day when we're practicing clinicians. We just somehow seems to forget it when we read the literature, that actually goes in the other direction. So if we think about the cause of a coin flip, that the coin is even, that it spins in the air, it's fairly a random event. And so we can get these kinds of outcomes just with, in a sense, no real observable cause. I mean, if you practice enough, you can probably flip the coin so it lands on heads all the time or tails all the time, whatever you want. But if we're just flipping a coin randomly, there kind of is no cause other than the balance of the coin and the physics, and then just the random distribution. We can actually compute these various probabilities out mathematically. And we know that on a fair coin, there is 1/2, 1/4, 1/8, 1/16, 1/32. So there's a 1 in 32 chance that we will get that sequence of heads. Or if we flip it 1,000,000 times, about a 32nd of the time, we'll get 5 heads in a row. So we can compute these probabilities in this deductive direction of logic where we have, say, a known truth, the fairness of the coin, or a known cause, or a known sensitivity of a test. Where you have a known truth, we can compute the various outcomes, the probabilities of the various outcomes. But that's actually not what we do in the real world. In the real world, we observe 5 heads, which is certainly possible on a fair coin. It's possible on a tails-biased coin. It's not as likely. And it's the only outcome on a 2-headed coin. What we're trying to do in the real world is if we observe 5 heads, we're trying to figure out the fairness of the coin. If we observe 65% one-visit success and 75% two-visit success, we observe that we're trying to infer the underlying truth of the success rate, which we don't know. We don't know the fairness of the coin. We don't know the actual success rate. And interestingly, from an inferential standpoint, you would think that, say, observing 5 heads in a row would provide you more information. But 5 heads in a row only rules out double tails. That's it. That's all that gets ruled out with 5 heads in a row. It could still be a tail-biased coin and give 5 heads in a row. Interestingly, these mixed sets, 1, 2, 3, 4, where you're getting a mix of tails and heads, you're actually able to rule out 2 possible causes. If you get heads and tails, you know you can't have a 2-headed coin, and you know you can't have a 2-tailed coin. And so it's a little counterintuitive that sometimes muddier data like that actually allows you to rule out other hypotheses. You know what it is not. And I got a section at the end that talks about, I hope to get to that, we talk about the art of not. So if you see mixed heads and tails, you don't necessarily know the fairness of the coin, but you know what it is not. You know that it's not a double-headed or double-tailed coin. So we talk about this in the CBCT text a little bit. And you may go and flip the coin 5 times in a row, and it actually, by chance, comes up 5 heads in a row. And the p-value of that is less than 0.05. Does that mean that that it's an unfair coin or it's a double-headed coin? I mean, these things can happen. So calculation of probabilities in this deductive direction doesn't help us, the p-values that we've all come to use in real life, doesn't help us as much as we would like to think it does. Because this can certainly happen. And this is not as far-fetched as it might seem. So, Molden Reed. Clinical and radiographic evaluation of 1 and 2-visit endodontic treatment in an asymptomatic necrotic tooth with AP, a randomized clinical trial. Sounds pretty impressive, doesn't it? Yeah? There's a consort diagram, and I was like, woo-woo, I'm excited about that. Because that's when you see that, it's like a little extra level of detail attention was paid to, like, this is the patient flow through the trial. And this was actually described as a classic classic T2 translation piece of research. And the underlying statistics that are used on this are basically Fisher's exact test, which guess what? Sits on basically coin flipping probability theory. So when we go look at a piece of research like this, and they were a little bit more sophisticated than this, but you can still say success and not success or failure. It's basically coin flipping from a probability standpoint. So let's take this project and we're going to run this in the computer before we actually run the experiment. That is, looking at prior probability in a completely different lens. What is the probability of getting a meaningful answer from this study before we run the study? Before we actually run the study, before we actually look at the evidence? What is the prior probability of getting a good answer or actually getting misinformed, getting the wrong answer? So here, I'm going to set the study up. This is the actual study numbers in the trial. They had 40 in the single visit group, or 49 in the single visit group, 40 in the two visit group, and we're going to assign the fairness of the coin in both groups at 70%. Is everybody with me so far? So we are going to work in the deductive direction. This is how Fisher's p-values work. And we're going to say, we're going to play God, and we're going to say the underlying truth of this study is both groups are equal at 70% success. Both coins are, shall we say, biased at 70%. We have two coins, a single visit coin and a two visit coin. And we're going to flip these coins 49 times in this group and 40 times in this group. What are the various outcomes of heads and tails of success and failure that we're likely to observe? This should make for some interesting math. Okay. So what is the prior probability of getting a meaningful result before we actually run the experiment? So this one I have a little video on, and then we can actually, if there's time and interest, we can play with it later. So here is, every time I click up here, it's going to run the trial again. And here is the actual observed successful outcomes and the actual observed percentage. So there's some variability with 49 flips of a coin at a 70% fair coin. You may not get exactly 70%. You might get 65 or 80 or something like that. There's going to be some natural variability that happens. And then we can look at the success difference that we should have observed. So we're off by 1% in the single visit case, and we actually landed exactly on the two visit case. And then the truth, the difference in between them is the truth is actually 0. The true difference is 0%, and our error is 1% because we were 1% off. Not bad, okay? In the computer, I can run this trial 1,000,000 times. And then we actually get to see what does the distribution of results actually look like. So we're going to start with a known fair coin. So click 71.83. That was a trial. 65.67. So actually in that one, in that trial, single visit did better. Just by random flipping of the coins. This is the underlying mathematics that is used for the analysis. This is it. It's the same underlying math. So 80.69. Each click is a run of the trial. Look at that. We got a 17% difference of single visit over two visit. That's a possible outcome that we could have observed. And coming up, we're going to do a distribution of them. So I'm just doing a couple of clicks to give you a sense of how this works. And they're going to mostly center around truth, but they're not always there. 14% off, 5% off, 10% in the other direction, 2% off. Click, 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 click. 17%. So we found in that trial, we found a 17% difference in outcome. So let's run this trial now 1,000 times. Actually, let's run it 10,000 times. 100,000, oh, that's 1,000,000 times. So we're going to run the trial 1,000,000 times. I couldn't remember what I typed in there. This is a video playing. So here we're going to run the trial 1,000,000 times. What's the various outcomes that we're going to do? And this takes 7 minutes to calculate, so we're going to skip to the end of it. Here we go. So here is a histogram that shows the range in successes that we observe, given that we know we started with equal success rates. So here, about 38% of the time, we're going to observe a difference between the two groups that have no difference of about 5%, about a third of the time. About 2/3 of the time, we're going to, by chance alone, observe a greater than 5% difference in the groups. Yeah, when there was no underlying difference. So what's the take home from this? If we actually do the clinical trial. Steve? I thought someone started to say something. You need a bigger N number. What if we actually do the clinical trial and we say that, you know, if there's only a 5% difference in the groups, we don't really care. Okay? How often is less than a 5% difference in these groups going to be observed when there actually was no difference? How often? 38% of the time. So let's just make it easy to do it. It's a third of the time. About 2/3 of the time, we're going to observe a greater than 5% difference when there actually was no difference between the group. So the prior probability of this trial actually answering the question is 1/3 correctly, and there's a 2/3 chance that we actually get, everybody say it, the wrong answer. The wrong answer. There's a 2/3 chance we get the wrong answer on this trial.
You need an experiment where the actual difference is much, much larger, not as small as it actually is.
That's next. Okay, so that's next. So this is really important from a clinical trial design standpoint. Why most published endodontic research is false. Well, this clinical trial that was heralded as a classic T2 translational piece of research actually has a 1/3 chance of finding no difference between these groups were there actually to be no difference, and a 2/3 chance of finding a difference between these two groups of over 5% when there was no underlying difference. In other words, there's 2/3 of a chance that this research is wrong. And I would say 2/3 is more than most. Most is 51%. This is 2/3, about. Yeah?
You don't know if you're in the 38.
No. No. It's worse. Yeah. So Eric points out that, again, you from what we call the confidence interval standpoint, this is a tangent issue, but you're on target. Confidence intervals are not well understood. Confidence intervals are widely thought of as if we have a 95% confidence interval, that is widely thought of as that being there's a 95% chance that the actual truth lands in there. And the answer is no. That's not what a confidence interval is. The actual truth is either in that confidence interval or not. It's either 0 or 1. A 95% confidence interval is if you ran the study 1,000,000 times, 95% of the confidence intervals would have the truth within it, 5% would not. So you actually don't know if you're in the 95% that have the right answer or the 5% that don't. Or here, you actually don't know if you're in the 38% that have the right answer, less than 5% difference, or you're in the 2/3 that don't. You don't know that. You just get misdirected. And you falsely, 2/3 of the time, assume that there's a difference when there actually was not. Prior probability. What are the chances, the prior probability of this research actually answering the question? The answer is 2/3 of the time it's going to be wrong. And it's a prior probability issue, and you don't even need to run the experiment to do that. Okay, now let's model in an actual 10% difference. And these were the numbers they observed. So let's take their numbers as truth for all time, that one visit successes were 65% and two visit successes were 75%. So we have played God, and we have two coins, and one's going to come up heads 65%, and one's going to come up heads 75%. And let's run the experiment and see what we observe, because we're going to get a range of heads and tails. What are we going to observe? So we'll do a couple of clicks. So that one there, interestingly, I bumped ahead. Sorry, folks. Good. So here, we actually observed 69% success in the one visit, although truth was 65, and we only observed 63 in the two visit, although truth was 75. And so we got an answer that was 7% to 17% off and in the wrong direction. Talk about getting it backwards. So single visit was better than two visit, and our actual observation was backwards, almost off by a fifth. So we're going to see what this distribution looks like as well of outcomes. Click, click, 65, 88. We got a big difference when it was bigger than it should have been. So these kinds of things are going to happen. So it's a sample size issue, Eric. You need thousands to get a good answer. 59, 83, big difference. Those look about the same. So we can see we can get quite a range of outcomes from a known truth, and we can get it backwards actually fairly often. So we want to think about this very clearly, because we're going in this deductive direction of probability, where we manipulate the known truth of the coin and we observe the outcomes, and that's actually not what we want to do. We want to go in the opposite direction. Let me look at my time. Good. Okay. So I'm going to jump ahead a little bit there. Good. So I actually played around with this in what's called a 2x2 contingency table, and I did the math to figure out what the actual difference would be to observe a statistically significant result. So we got a statistically significant result here. And so to observe that, you would need to have almost a 30% difference in the actual, in the observed success rate to see a difference in 10% success. So it overstates the success rate fairly dramatically when you have a small sample size. Sorry if that section was a little rough. I hope it worked out, but I want to get to a couple steps in perception and cognition too. Hurricanes and hurricanes, another probability issue, and it was actually timely. I had this stuff in there before Irma swept into town. So this paper, female hurricanes are deadlier than male hurricanes. To test this hypothesis, we used archival data on actual fatalities caused by hurricanes from 1950 to 2012, so on and so forth. 9 independent coders who were blind to the hypothesis related the masculinity versus the femininity of the historical hurricane names from 1 to 11. They did a binomial regression analysis. I don't even know what that is. But what they did do was they made a big mistake. They published their data set. Now, what might we want to know before inferring that female hurricanes are deadlier than male hurricanes that's on target with this lecture? The prior probability of what? Of female hurricanes. What is the prior probability of female hurricanes? So I looked. Okay, 1950, Easy, King, 52. Abel, Barbara, Florence, this is 53. 54, Edna, Hazel, Connie, Diane, Ione, Flossie, Helen, Deborah, Gracie. I'm not done. 1960s, Isabel, Betsy, Alma, Inez, Belula, Gladys. Do you hear any male names in there? They didn't start naming male hurricanes until 1980. There's 30 years of female-only hurricane names. What do we think we're going to observe? This is in PNAS. This is peer-reviewed. Peer-reviewed. So there were only female-named hurricanes from about 1950 until 1979. And I'll get to that. So why did the naming change? Now, I want to split the group into under 40 and over 40. So over 40 answers second. Under 40 answers first. All right? So, himicanes, proposed by Lib Backer, Sarasota Journal, Wednesday, April 1st, 1970. This isn't a joke either. Hurricane names have lib and a hal. Under 40. What's a lib? Women's libber. You're an over 40 though. Under 40. You guys have never heard of a women's libber, have you? Under 40, who's heard of a women's libber? Over 50, who's heard of a women's libber? All of those hands go up. That's what it's referring to. You know now. Women's lib. The movement was successful. We don't hear about it anymore. So she says, her name is Roxy something or other, Roxy something. Roxy Bolton. Roxy says, women are not disasters, destroying life and devastating effect in community, leaving a lasting and devastating effect, she said, demanding hurricanes be called something else. Robbie told me not to throw that in there. He voted for her. So in 1950, 51, and 52, hurricanes and tropical storms were named using the military phonetic alphabet. The switch was made to all female names in 1953. Many feminists decried the sexism, with Roxy Bolton noting that women are not disasters destroying life. The switch to the current system in female names was made in 1979. Now here's the key bit. In the pre-1979 era, basically all female data, the number of average deaths per hurricane was 29.1, and after that it was 16.2. So the prior probability of female names, it dominated, because it was 30 years of basically female-only names. And as it turns out, those storms were more fatal, but they were all female names in that time. What do you think the outcome's going to be? Does it have anything to do with like people not paying attention to the hurricane name because it's a female name, and male names are more threatening and they're more likely to evacuate? Those are really advanced in that paper. So hurricanes and himicanes, prior probability dominated the outcome. There's a whole host of reasons why the earlier hurricanes might have been more deadly. The infrastructure is weaker, there was less advanced warning, those hurricanes tended to be stronger than the average category, and so on and so forth. So I'm going to skip the prosecutor's fallacy because I actually want to get on to some CBCT stuff. The San Diego Strangler, I didn't kill my babies. Ken, you and I can dink around with this. Lance Armstrong, business in the math student. Yeah, this would be good. Gary wanted me to do some examples from medicine too. So I want to get on to some CBCT stuff, but I want to really drive home prior probability, likelihood, posterior probability. All right. So it's these three gears that have to turn. Yeah, we're going to be fine. You've got to have all three of these pieces of the puzzle to make the inferential engine work. So let's look at a pregnancy test. So what's the purpose of the pregnancy test? Well, we want to know, do we have a baby or not? Okay. So here's a pregnancy test, and it's supposed to look like that, and it looks like that, and it's supposed to look like that, and it looks like that. Now, so this is what? What gear is this? What gear is this? The pregnancy test is what? It's the evidence. It's the likelihood. Who are we testing? And is she pregnant? The test is the likelihood. And this, we heard it, and we're getting some of the language now, but a very common mistake is to mistake the likelihood for the posterior probability, to say that the test is the outcome. And this test isn't clear. Let's go through it. I'm glad I'm hitting this example. Good. So, young woman gets this test, and the results look like this. The evidence looks like this. And we're really still not quite so sure if she's pregnant, because this isn't what I would call clear and compelling evidence. Agreed? So our prior probability is this young girl here, and she gets the test, and we're not sure if she's pregnant. Okay? So we need to sum these things up. The prior probability, this is going to make sense in a second, plus the test, that equals the posterior probability, the likelihood that she's pregnant. All right? So there's nothing to prevent an old lady from doing the exact same test, right? Oh. So we take the old lady, and she gets that test result. What is the probability that she's pregnant? It's possible, but it's lower. And it had nothing to do with the test, did it? Because it's the same data, it's the same evidence, it's the same likelihood. What happened was the prior probability was different. So we're not quite sure, but we're thinking, nah, not so much. We're not thinking so much. Okay? Okay, now we have what we're going to call a more clear and compelling test. Our evidence is better. And so this is yes, no. Okay, this is a better test that's internally somehow figured out to do a better job. And now we can be pretty sure that she's pregnant. What about the old lady? Are we buying it? Pardon? This is a more accurate test. It's a more accurate test because the tests have gotten better, and this is a more accurate test. And also, we don't know that. All we know as the evidence on this test appears more clear and compelling. There's no hint of fuzzy pregnant. It's like pregnant. The digital readout, okay? I'm making this a pure example, and that's correct, and we can talk about it some more afterwards, Charlie. Okay, you're commingling things. Okay, so this test here says pregnant. What would it be reasonable to interpret this as ambiguous, whereas this one is easy to interpret as ambiguous? That's your evidence. Your evidence is not clear here, and your evidence, because you don't know the sensitivity and specificity of these tests. Okay? If you do, you can run Bayes' theorem and calculate it, but you don't know that. All you have here is this one says pregnant. I got a thumb forward again. Thanks, Charlie, for making me click through the slide again. All you have here is this piece of evidence, which says what? Why would you think anything different? The other one may not, the other one isn't accurate. Yeah. Okay. Well, what's your evidence? Is there any evidence that she's not pregnant here in this test? No. The other test, there's some. It's not clear. The bands aren't light. This test, there isn't. So interpret the test as the test result sits up there. And still, here, the old lady, are we buying it? No. No. No, the prior dominated. And so what happens if I give this test to Ken? The prior dominated. So given the same test result, okay, there's no chance. The prior dominated. So we want to separate these three pieces out. In the pregnancy test, we're not normally thinking of the prior probability because guys and old ladies don't usually do this. But I wanted to use this toy example to show you how, given the same evidence, and we can pick it apart if you want, but given the same exact evidence, the test says the same. That says pregnant. It doesn't say anything else, and it's not gray. We have a different posterior probability of pregnancy that had nothing to do with the test. It was dominated by the prior probability. Yeah.
Kind of like when you purposely cold test a root canal treated tooth in the patient, and they say, I feel it.
Exactly. Okay, how does that affect us with image interpretation? And I got to give Gary his time, but I actually want to do this. And Bobby Schlossberg is going to escape this one. All right, so I knew based on work that had been done in medicine, this is a little bit of a recap, but I want to tie this because this is a prior probability issue. I knew that work that had been done in medicine, that the prior probability issues affected the image interpretation. And so we played around with this a few times at the TDO meetings, but we actually got two pilots and then a real project that we sent out with these two periapical areas are pixel for pixel identical. And people's calls on these pixel for pixel likelihoods, because we asked for an interpretation of the periapical areas, was dominated by the prior probability, which is the crappy endo or the virgin tooth. Pardon? Horrible. Actually, this one's not horrible. This one's just marginal. Yeah, heinous. So what happened here was we went in the unaltered case. We went from a possibly, and I could certainly call that a possibly, but it's a young person, maybe they're post-ortho, something like that. These people, I don't know what they're looking at. And even more worrisome was a third of our participants failed our control cases, which were like these. So we went from 12% calling this definitely abnormal here to half the people, 40%, calling it definitely abnormal here. And it had nothing to do with any changes in the periapical area at all. It had everything to do with the prior probability issues, which hit us as endodontists very, very fast in the image interpretation process. So you actually kind of want to look at a tooth like this. And Ken, you did this at the AAE, didn't you? You masked out. You might play with that again. Ken masked out this portion of the case right here. And I'll tell you, all of a sudden, you're not so sure about the interpretation anymore. So this is very easy to call this a finding. And you may be tempered here, but the tempering here has got nothing to do with the finding. It's got to do with this is a virgin tooth, and I'm not expecting anything. And an expectation is a prior probability, okay? So we saw these big swings. So we went from all of these definitely normal, possibly abnormal. We went from those findings to almost all definitely abnormal findings. We saw big changes in the swings in people's calls. I want to do Bob's study quickly. Bob Grover, he talked last year, didn't he? Yeah. So Bob talked about his outcome research, and I looked at his slides, and I said, we got a problem with the slides, Bob. I wasn't sure if Bob knew it at the time, so I sat down with him afterwards. And so here was Bob's plot of extractions of cracked teeth versus the years. Everybody see that? What are the prior probability issues that Bob faces in this study? Ken,
Just extraction. Well, the fact that he gets told that they get expected.
that's fine. But remember, these are observations of cracked teeth, and this is a count of the numbers of cracked teeth. So there's 14 cracked teeth here. What's the prior probability issue? Anybody? Go ahead, Lena. No. What's the prior probability issue? Gary, you want to take a stab at it?
I don't know.
Total extraction?
There you go. You're on the right track. What was the number of observations per year in each one of these categories? What was the number of observations? So let's just make some numbers up because I got to wrap this up. If we had 100 observations per year across all of these years, and this was the distribution we found, it would be fair. Agreed? if there was 100 observations per year, from years 1 had 100 observed teeth, all the way out to year 20 had 100 observed teeth, this would be fair. But what if he observed 1,500 teeth in the first 3 years, and the remaining 1,000 teeth were from year 5 on? What if he only observed 19 teeth out here? That's a 5% crack rate. And what if he observed 700 teeth in year 1? That's a 0.3% crack rate. So the prior probability issue is how many teeth did he observe in each one of these years that resulted in X number of cracks? If 10% of the teeth were cracked and we observed 100 teeth every year, we'd see how many cracked teeth a year? 10, right? If in the first year we observed 700 teeth and 10% were cracked, we're going to observe 70 cracked teeth. And out here at year 20, we observed 20 teeth and only 1 was cracked. So the prior probability issue that Bob had was what was the base rate of the number of observations per year that he had. And when you do that, I ran the data. So here's the actual number of observations. So in year 1, he had 375 observations. In year 2, he had 400 observations. So there were 400 teeth at year 2 and 7 cracked. That's a very, very different picture. This is the same thing as the smokers. 10% of the Londoners were smokers. That's 100,000 smokers. Versus 75% of the Londoners are smokers. That's 750,000 smokers. And you actually get a backwards answer. Smoking reduces lung cancer risk when you fail to take the base rates into account. Okay? That's why this stuff is so important. So here is the actual corrected numbers here. So the raw cracked count. So year 2 is great, and so is year 20. Year 2, he observed 7 fractures, but the percentage of fractures was under 2%. And out here at year 20, where he only observed 1 fracture, there were only 20 observations, and so that's all of a sudden a 5% fracture rate. And again, there's a lot of noise in the data. With 20 coin flips, you're not going to have a good observation, and we're not going to get there today. But this was a prior probability issue that I looked at in Bob's data, and I'm like, Bob, you can't report data like that. That's misleading because it makes it look like we got a bunch of cracks down here at these early years. I said, this is not painting a compelling picture for this. It makes it look like we got a bunch of cracks down here at these early years. And the fact is, the actual curve is down here at these early years, the teeth don't crack. That's these purple bars. The teeth don't crack. The cracks happen year 5, 6, and go up and then tail off. But again, out here, there's a lot of noise in the data because the number of observations are so small. He only had, how many observations did he have out here? He had like 14 observations here and maybe 19 observations here, so there weren't very many observations. Okay. I think that's it, and I'm going to let Gary go now, unless there's questions. So it's the 3 pieces. You've got to identify the prior probability issues, or you're going to get backwards estimates on the posterior probability. You ready? Yes.
Let's go back. I want to go over some of the cases that we did when we presented the cone beam data, because it goes to this issue of prior probability, and I hope it'll help you understand it a little better. It's something that John saw immediately. This is about prior probability. So what the claim I was making is that you could take cone beam if you took a cone beam radiograph, you could look at if you look very, very carefully at, say, a tooth like this, you could actually figure out what the anatomy was. And I used this particular tooth as a case. So we did the cone beam imaging, then I took the tooth out and I extracted it and we x-rayed it from various angles. I have to laugh at this. And then we cleared it and I could see I knew what the anatomy was. And then I go back to the cone beam and I say, you know, if you go through the cone beam, you can actually see what all this anatomy is. Well, I knew what the anatomy was ahead of time. Okay, so let's actually take a look at it. As you go through this is a video it's playing. Can you see my mouse? Okay, I want you to look right here. This is what we're looking at. So I'm looking at this dot. See this dot going? Oh, well, you can see lateral canals on the cone beam. And I'm thinking this thing is going to revolutionize. I know we can figure out completely all the anatomy. Then we look at this, and I go through it, and I can see exactly what the cleared tooth showed. And don't laugh because all of you were impressed with this. And John is just steam is coming up off of his head as he's watching this, I'm sure. He's never really said so, but. And then we'll look at this one. Look at, I can see where it goes, and I could figure it out. It goes to the distal lingual. I knew exactly what direction, where it was, which root. And I'm thinking, I'm going to be able to do this on every tooth that I do. So this is what's called prior probability. I already knew ahead of time. So now if you try to figure this out and find this anatomy in cases where you don't know ahead of time, there's so many false positives that you don't really gain a lot of information. And false negatives, correct. Okay.
That's a very common error in the academic evidential base, that they'll do the CBCT study, and it's classically done as a burr hole study, and they'll drill the burr hole on the distal root of the lower molar, and then they'll find a section that lines that up, and then they'll put an arrow to that section, and then they'll ask the observer, do you see the burr hole on the root end? This is how that work is classically done. You can't do it that way.
That's exactly what we did. I took these teeth, I extracted the teeth, I drilled burr holes in the thing, and then I ask all of you, now this is a periapical radiograph. Can you see where I did the burr hole? No, you can't, because everybody guessed wrong when I presented this. It's really there. And then I showed the cone beam. Look, you can see it on the cone beam. And you can't see it here. Look how clear it is. So exactly as Jen said, I did exactly. And then I said, well, how small a hole could we make that you could, how small does the hole have to be before you can't detect it with the cone beam? So I took different sized drills, and we drilled it into the lateral cortical plate, different sizes, burrs, and then we took cone beams and said, well, how small does it have to be? You couldn't see them at all on the periapical. There's no evidence of any hole. And then we took, I can see it here. I can see it here. So, Jen, you are really very kind to me. I'm forever grateful for that. So that's the inference that was made. Okay. Last thing, because I want to give a quiz. I want to give a pop quiz here. And we did the same thing with this. The same prior probability issues that involved so much work. We did histological measurements, and then I saw if they matched up against the cone beam, and this one even had more problems because you can take these sections of things and you can find, this thing was 3.4 millimeters by 1.9. Well, I could take a histological section and find that if I took enough sections, so it was completely meaningless research, really, so, but an unbelievable amount of work. I think, and that's why I think we need to moderate our criticism of some of this work, because even if it's very poorly done or the inferences are very poor, it's still a lot of work that these people do and dedicate their lives to trying to improve our knowledge. So, okay, so this is the last case. This is the quiz. This was a real patient, and it looked like maybe a class 2 ECIR. There it was clinically. There's a little thing on the lingual. And then I took a cone beam, and I'm looking at this thinking, you know, and the cone beam shows me that this isn't a class 2. It's a class 4. And I'm not going to get involved in surgery because this thing goes more than halfway down the lingual side of the root. And then I take these cone beams and I see all these little things. And I'm running through the sections here now. Take a look at what I'm looking at here, all of this stuff. And I'm seeing the extent of that resorption as you go through this, all this stuff. Now, what you know about prior probabilities in cone beam imaging, how likely is it that that is really the extent of the lesion? Can you use the cone beam imaging to actually detect how extensive this lesion is? What do you think? I'm not sure we need a binary answer there. What is the prior probability, do you think? Let me show you the tooth. That's the tooth, the cleared tooth. So this goes to, I don't know, I'm interested in John's take on this. This is my take. When you try to read the cone beam in the way that I was doing there, where you think you see these things, it isn't that you're right or wrong. It's going to be, there's going to be a percentage of the time when it's right. In this particular case, it was right. But there's going to be sometimes when you're wrong, when you see things that your brain is just making up, and the cone beam doesn't give us that kind of certainty about what it is that we're seeing. And I think the more experience you have with cone beam, your error rate is likely to go down and not be misled by false positives or false negatives. But you're never going to eliminate those things. What's your take on that, John?
I was thinking of it from the standpoint of the prior probability issue that I solved was one of image resolution. And the analogy that we use to explain that is you go to a lake and you want to measure the size of the fish. You run your imaging and you want to see the extent of the absorption. And if your net for measuring the size of the fish has holes in it that are 3 inches across, you're probably not going to catch any 2-inch fish. And you're going to erroneously conclude that all the fish that you see are 3 inches or greater. If your imaging device has a resolution of 76 microns, you're probably not going to see the anatomy that's smaller than 76 microns. The prior probability of that is low. It's actually a little more complicated than that. It gives people a sense of it. And so knowing what these look like on a histological level, that they can be quite a bit smaller than that, and there are changes that may be even smaller than that. The probability that we're going to, the prior probability that we're going to see the full extent of the resorption is really zero. I think we're going to see more of it because with CBCT, the net is smaller than with cone beam, the PA radioactive, so we're going to pick up more. Our netting is smaller with CBCT than it is with PA radioactive. But that smaller net is also going to pick up a lot of moss and algae and bottom dweller fish and beer cans and other stuff that we don't want, that we might mistake for fish. We might mistake for so it's tricky. There's no way to trade. Every time you want to call more resorptive defect, you're going to increase the chances that you fall positive for stuff. There's always a trade-off between those two. That's why hard to see this. Larry?
Yeah, so let's ask the group, given what you know now, given that you have this cone beam evidence, how many of you, do you all agree if it's a class 2, might be a good idea to flap it lingually and see if you can do it, but if it's a class 4, you should probably leave it alone. How many of, what clinical decision do you make in this, and how much credence would you give the cone beam imaging that I showed? Because at the end of the day, we're interested in your decision making on this case. That makes, don't be afraid. You want to look at the CBCT? She wants to see it.
I saw something that you didn't show.
Okay. You want to see
I want to see the sagittal.
No, can I just ask with that, you don't be looking at the age of the patient and any chronological you're not including that in the decision making?
No. No, let's assume, in fact, this was actually an attorney for Qualcomm, and I think he was about 45 years old. Yeah. What do you want to see?
Because I, in that one slice,
The point is, you already know, I guess the point we're making, you already know that the resorptive thing, and no matter how many slices I show you, you're going to see it. Now you're going to see it.
And you can see it on the PA.
On the, you can't see the apical extent of it, though, I don't
You
think.
can see it going farther down. I mean, looking at your micro CT, I see stuff here and here.
Yeah, now, yeah.
I wasn't so sure about that.
Yeah.
But once I saw the micro CT, it's like, oh, it's going down the roots. It's,
Gary, you know, it's a two-edged sword because, you know, if it didn't require our inferences, we could write software to find these things.
Yeah.
You know, in Afghanistan, the military has tons of satellite data of the countryside. They're looking for terrorist camps. Well, they write software to find them, but they can't do that. And so they find things. They don't know if it's some, you know, goat herders camp or if it's some rock outcropping, but it'll find things based on their algorithms. And then they have to get human eyes on it to kind of give a little bit of inference to it.
Yeah.
And so we rely on that tremendously, but then we have to recognize how the machinery works so that we're not, you know, being fooled.
You know, yeah, you're right. And I just think it's interesting now because this group has, well, this was 8 years ago, and this group has now experience with this device, and it's just interesting to see how much more sophisticated we are now using this and understanding what its limitations were instead of 8 years ago thinking that it was going to solve all our problems. So I want to thank John for the extraordinary effort he made to do this. I think he did a tremendous job. These are difficult concepts. You're not going to get them all just sitting there. You're going to have to go home and think about this and read about it. And then when these studies come up and you look at it, the first thing that pops in your mind, what is the prior probability? How are they looking at the likelihoods? Are we confusing one for the other? And after you do this for about 6 months, it'll really start to make sense for you. So thank you, John.